Good morning. Today I'm going to talk about Fourier transform, and in this next 1 hour we'll basically do an introduction on Fourier transform. So who's Fourier? Fourier basically is a French mathematician born in the 18th century. He's very famous. The word Fourier exists in many mathematical literature. For our case, it's like Fourier transform, Fourier series, things like and what he did was that he generated some equations which can represent any periodic functions as simple with additions of sinusoids. And currently, the Fourier series, Fourier transform analysis and synthesis is used in many branches of science and maths. So let's come to some details of what is Fourier analysis and synthesis. The word Fourier, of course, is his name. The word analysis and synthesis now will explain. Analysis in this example means, for our case, we assume that the input signal to our system or our Fourier analysis machine is a continuous time signal. In another course, at third year, you might study it as a discrete time signal. But here, let us now assume that we are studying for the signal x of t, which is a continuous time, where t is continuous time. The word analysis here is to decompose the original signal x of t into cosine waves. That's it. To analyze a signal using Fourier means to decompose the original signal x of t into cosine waves. Later on, you'll realize that cosine waves can be also represented as complex exponential, and therefore, whether we break it into cosine waves or complex exponentials or even sine waves, it is actually all the same. When we decompose x of t into cosine waves, we are basically representing it into its frequency domain. What is frequency domain in this case? By frequency domain means we now know x of t is composed of what signal, what cosine waves at which frequency. So specifically, given an unknown signal x of t, we break it down into cosine waves. We find out how many cosine waves are needed to construct the original x of t, and for each cosine wave, which frequency is it in, what is its magnitude, and what is its phase. With that understanding, then we can now reconstruct x of t. That is the business of the synthesis. Given the frequency representation which was generated by the analysis, we generate the original signal back in time domain by adding up all the cosine waves that we have known. Of course, how many cosine waves there is left for us to figure it out? What is the magnitude of each cosine wave is our problem. What is the phase of the cosine wave, and the frequency is all our problem in the analysis. We now have a simple figure to show what we mean. Here, x of t is represented by this orange box. This is being sent into the Fourier analysis machine. X of t is a time domain representation as shown below. The green graph is x of t. In this example, it is a periodic function. The horizontal axis is time, and the vertical axis is simply x of t. In this example, we have a continuous time periodic signal. This continuous time periodic signal x of t is sent to a Fourier analysis machine to generate a frequency representation. Remember, we say that a frequency representation is nothing but representing the original x of t by the number of cosine waves that it has, at which frequency and which amplitude, and as well as its phase. Here, I have two graphs. One graph showing the amplitude of the cosine wave, the The horizontal axis is the frequency. In this figure, it clearly shows that I have 4 signals. The second graph, later on you will see, is the phase. Along with these 4 amplitude of this cosine wave, I also show you the phase. Since you know the amplitude, the phase, as well as the frequency, as well as the number of cosine wave, you can perfectly reconstruct the original signal back by the Fourier synthesis machine. The Fourier synthesis machine is nothing but adding up these 4, in this example, these 4 cosine waves up, and then we reconstruct perfectly. What Fourier has told us is that for periodic signal, we can decompose into sum of cosine waves. Let us now have another example. In this example, I will write it down for you. And in this example, I am given x of t, and x of t is given by some equation. It has a DC term, a constant, 10, and it has some cosine term, 3 cosine 2 pi 10 t. So it is basically a cosine wave at frequency equals to 10 Hertz. It has an amplitude of 3. Sometimes we prefer it to call it a magnitude, and the phase is equals to 0. So in this example, you now have 2 components making up of the original signal. A DC term, which is a constant term, and a cosine wave. Let us make our example slightly more complicated by adding some more cosine waves. 5 cosine 2 pi 20t plus pi over 3. Now I have just added one more cosine wave with magnitude 5, frequency 20 Hertz, and a phase shift of pi over 3. And the last term I'm going to add is a sine term, plus 4 sine 2 pi 30t. And in the last term, I have a magnitude of 4, frequency of 30 Hertz. But this time, interestingly, I did not add a cosine wave. I added a sine wave with phase shift of 0. Remember that if I'm given this equation, I can of course plot x of t, and x of t looks like a periodic signal because when you add all these 4 components up, the signal remains periodic. However, Fourier asks us to decompose our original signal into cosine wave. So how do we decompose 10 into cosine? It's 10 cosine 2 pi 0, and that is the trick. A DC is simply a frequency with 0 Hertz, and it does not change. So this is interesting. We now realize how to change a DC term into a cosine representation. The magnitude remains the same, and the frequency is simply 0 because 2 pi 0t for all t remains 0, cosine of 0 is 1, so the constant remains. The second term is easy enough. In the second term, it is exactly the form that we need. So let's write it down. It is the magnitude multiplied by a cosine term, 2 pi, we have the frequency, 10t, and now we add explicitly that the phase is 0. So if so, previously we also have to add phase is 0. What about the third term? The third term again is identical to in fact, the third term is the easiest of them all. The third term has already given you the magnitude in the cosine representation with the frequency of interest. Additionally, he has already told you his phase. So the third term has all the information that we need. It is the magnitude, the frequency, as well as the phase in a cosine representation. And in the last of our signal, which is this one, which is quite interesting. It is a sine, but remember that we're not interested in sine. We want to represent it as cosine. So sine is nothing but a time-delayed version of a cosine. In other words, we're saying that sine t, sine 2 pi ft is equals to cosine 2 pi ft minus pi over 2. We know that cosines are a phase-delayed version of the sine. And therefore now we can write our equation of 4 sine 2 pi 30t in cosine as 4 cosine 2 pi 30t minus pi over 2. And now we have reached here. We have changed our original equation into a Fourier series representation. A Fourier series representation tells us the number of cosine we need, or number of terms we need, or number of sinusoids we need, at which frequency, and for each frequency, what is the magnitude and phase. So let us now look at the slide, and I will repeat briefly. We have the equation over here, the original equation with 4 terms, the DC term, the cosine term, the second cosine term with a phase shift of pi over 3, and the last term, the fourth term, is a sine term. We have just gone through the exercise of converting these 4 terms into cosine representation. And this is the answer. With this, we now can write what we mean by a frequency domain representation. We now can see that there are 4 terms. These 4 terms at which frequency? The first one is 0, the second one is 10, the third one is 20, and the last one is 30. And at each of these frequency is corresponding magnitude and phase. So in fact, in this blue highlighted region, I show you that the frequency representation of my original signal is nothing but saying that there are 4 cosine waves at all these frequency with this amplitude and this phase. Once we understand this, we can sketch the frequency domain representation. In this figure, this is another way to view the Fourier analysis. On the left, the green curves is x of t. The x-axis or the horizontal axis is time. The vertical axis is the magnitude. And here it shows that the figure has a DC offset at 10, and it will go to the bottom at 2 and go to the top at 18. It looks periodic, and we use the Fourier analysis to analyze, and we saw that there were 4 different components. We plot this component now. At 0 Hertz, it is a nothing but a straight line with amplitude 10, as in this equation here. The first one, 10 cosine 2 pi 0 t plus 0. I then sketch the second, third, and fourth term over here. So this is a second term, which is a cosine at 10 Hertz with amplitude 3, no phase shift. The third one is a cosine at 20 Hertz with a phase shift of pi over 3 and amplitude of 5. And the last one is a sinusoid, a sine, but here I explicitly write it as a cosine with 30 Hertz and a phase shift of minus pi over 2 and an amplitude of 4. So these four are the components of this. In other words, if I add these four up, you will become this guy. So now you have seen in this representation, these four components, what is a more compact way to represent this? One compact way, of course, is nothing but listing it down as a list of an array of terms, and each of these terms represent one cosine wave. That's one way. And in fact, when I did my program writing this generation, I have an array of cosine waves with these three elements. However, in digital signal processing and in most mathematical representation, we're going to represent it in a graph. In this graph, the x-axis is frequency now, as opposed to in this previous graph, the x-axis, the horizontal axis, is time. So that's why we call this representation time representation. In this figure, the horizontal axis is the frequency, and therefore we call this the frequency representation of the signal. Why do we say that this is a frequency representation of the signal? Right, remember we have four graphs. Each one of the graph represents one cosine wave. Let us see how do we represent these four graphs into these two graphs. The top graph, the vertical axis, is called the magnitude. Here, the vertical axis is called the phase. These two graphs added together represents the magnitude and the phase of a cosine wave at this particular frequency. So I have, let's look at the first one. I have 10 at frequency 0 with a phase shift of 0. This represents the first graph. The second graph, I have a frequency of 10 with a magnitude of 3 and a phase of 0. This represents the second graph. In the third graph, I have a magnitude of 5 at frequency 20 Hertz with a phase shift of plus pi over 3, and this represents the third graph. And finally, in the last graph, I have a magnitude of 4 at the frequency of 30 Hertz with a phase shift of minus pi over 2 to represent this red graph, which is the last term, the sinusoid or the sine term. And please remember now that in our maths or in our DSP, we always represent the analysis in this graphical form, one graph showing the magnitude and the other graph showing the phase. After we have done the Fourier analysis, let us now clearly understand what does it mean for us. If you look at these two figures, the idea is that now you can very quickly figure out where are the components of the signals. Oh, it is at 0 Hertz, 10 Hertz, 20, and 30 Hertz. Which of the components are large? Okay, the 0 Hertz is large, as well as the 20 Hertz is large. In fact, most of them are 0. So if you look at this representation, this is definitely a much more compact way, intuitive way, as well as a clever way to understand the original signal x of t in time domain. Because in this graph, x of t, all you can figure out is it is slightly periodic, it has an offset of 10, and it goes up and down, but you have no idea what kind of signal it contains. With this graph, you can clearly know where are the frequencies and how important each frequency is. For example, in this example, how important means the larger the magnitude of the signal, the more important it is, I guess, to reconstruct the original signal. Right, so we have the analysis now. I, of course, did not tell you how we did this in an arbitrary signal. In this previous example, it was very easy. We have the original equations and we can keep on manipulating to get the cosine. In other example, our life is not so simple, but the process is the same. Okay, somehow we will be using the Fourier analysis equation to break the original signal into this form, to find out the magnitude and the phase at the particular frequency for all frequency of interest. Given the analysis, now what can we do? We can reconstruct the signal. So the idea is this: if I have only given you the frequency domain representation, then for each of these lines, you can take the magnitude, the frequency, and the phase and generate a graph. The second one, you generate the second graph. The third one, the third graph, and the fourth one, the last graph. And remember, since we have decomposed it, all we need to do is to add them up, and then we get the original signal of interest, x of t. So you have just seen Fourier analysis and synthesis.